Imagine for a second spending like $600 an hour just to simulate a single background character in a video game.
Right, yeah, just one character.
Exactly. A character that just walks around a virtual town and, maybe buys a digital coffee. A year ago, that was the absolute bleeding edge reality of AI research.
It really was. It was incredibly expensive.
But today, that exact same simulation costs about $60. And by next year, it'll cost the same as dropping quarters into a Pac-Man arcade cabinet. So, welcome to the era of low-cost cognition.
It is a macroeconomic shift that is happening faster than really anything we saw with the personal computer or the internet.
Oh, absolutely.
And it fundamentally changes how anyone who is building a business or writing software or even just managing a team needs to operate on a daily basis.
Which brings us to our mission for today's deep dive. We are unpacking this massive, incredibly dense, battle-tested guide called What We've Learned from a Year of Building with LLMs, specifically applied LLMs.
Yeah, and this isn't just theoretical fluff.
No, not at all. It was published in June of 2024 by this powerhouse team of AI researchers and engineers who are actually in the trenches. Folks like Eugene Yan, Brian Bischoff, Charles Fry.
Hamal Hussein, Jason Liu, Shreya Shankar. Yeah, these are the people who have been tasked with taking the theoretical magic of large language models and trying to force them to actually be useful.
Right, useful in the messy, unforgiving reality of enterprise software, which is so much harder than it looks on Twitter.
Oh, definitely.
And for you listening right now, whether you are a developer prepping for a sprint, a founder wondering where to spend your venture capital, or just someone trying to understand the actual mechanics behind the, estimated $200 billion AI hype cycle.
Give or take, yeah. It's a massive number.
Right. Well, this is your shortcut because there's a massive gulf between a flashy demo and a sticky product. I mean, it is so easy to build a weekend AI project that looks like an absolute miracle.
You hook up an API, you write a clever paragraph of instructions, and boom, your app summarizes a PDF perfectly.
Exactly. But trying to make that exact same AI behave predictably on, a Tuesday afternoon when real customers are slamming it with weird edge cases and typos and adversarial prompts.
That is a nightmare. It really is.
It is. You don't want to overwhelm your user, and you certainly don't want to bankrupt your company paying for compute costs.
Right. The transition from demo to production is where the illusion of the quote-unquote smart AI totally drops.
Yeah, the curtain gets pulled back.
Exactly. You realize you aren't dealing with an intelligent colleague. You are dealing with a highly capable but, intensely chaotic statistical engine.
Chaotic is the perfect word for it.
Yeah. And the authors of this guide break the challenge of taming that engine into 3 distinct layers. First, we have the tactical layer, which covers the absolute nuts and bolts of prompting and injecting data.
Okay, the foundation.
Right. Then we have the operational layer, dealing with day-to-day workflows, team dynamics, and the incredibly difficult science of evaluating if your model is actually doing what you think it's doing.
Which we will get to because that is fascinating.
And finally, the strategic layer, which is all about long-term survival and building competitive moats.
So let's start right at the foundation, that tactical layer. Before we can even dream of building some massive scaling AI product that takes over the world, we have to master the absolute basics of communicating with these models.
Yeah, the prompting.
Right, because I used to think prompting was just, typing a clear sentence into a text box, just asking nicely.
A lot of people still do.
Yeah, but the guide treats the prompt as your foundational system architecture. And they insist on a few non-negotiable fundamentals, starting with end-shot prompting, providing examples.
In-context learning, that's the technical term. And they are very rigid about this. You need an N of at least 5, like 5 representative examples.
Wait, let me unpack that word representative, because if I'm building an AI that summarizes movies and I just feed it 5 examples of how to summarize romantic comedies,
it's going to fail.
Right. I'm assuming it's going to struggle when a user asks it to summarize a horror film. Why does it over-anchor like that?
Well, to understand that, you have to picture how the model maps concepts in its latent space. A large language model doesn't actually understand romance or horror.
Right. It's just math.
Exactly. It understands mathematical proximity between tokens. So when you provide 5 examples of romantic comedies in the prompt, you are mathematically steering the model's attention mechanism into a very specific, narrow cul-de-sac of its training data.
Oh, wow. A cul-de-sac.
Yeah, you are tightening the probability distribution around words associated with romance. So when the horror prompt comes in, The model is already heavily biased toward the vocabulary and structure of a rom-com.
So it's basically already thinking about meet-cutes and weddings before it even reads the horror script.
Precisely. Its ability to generalize just collapses because you accidentally fenced it in.
Okay, so you have to curate those 5 examples to cover the entire surface area of what your users might actually ask for in production. Action, horror, documentary, foreign films, all of it.
Right. And beyond just the variety of the content, you have to demonstrate the specific behaviors you want.
Behaviors. Like what?
Like, if you expect your LLM to realize it doesn't know the answer and then decide to use a tool, maybe querying a SQL database or calling a weather API, you cannot just tell it, hey, use tools when necessary.
That's too vague.
Way too vague. You have to literally show it an example in the prompt where a hypothetical user asks the question, the assistant outputs the syntax to call the weather API, receives the mock data, and then answers.
You are basically building a mathematical template for success.
Exactly. Show, don't just tell.
Okay, that makes sense. But then we get to the concept of chain of thought prompting, COT. Because for the longest time, the big hack on Twitter was just to append the phrase, think step by step to the end of your prompt.
Yeah, the zero-shot code 2 trick.
Right, but the authors are saying that's practically dead advice for production systems today.
It is. Think step by step is entirely too vague when you have an actual business process on the line. The authors advocate for giving the model a highly structured, metaphorical sketchpad.
A sketchpad. Let's break down the mechanics of that, because an LLM is basically the world's most advanced autocomplete, right?
It's a good way to look at it.
It predicts the next word based on the words that came before it. So if I ask it to summarize a complex legal transcript, and it immediately starts outputting the final summary, it's only using my original question and the raw transcript as the context to predict those summary words.
You're hitting on the exact mechanism there. And that's why immediate generation often leads to hallucinations.
Because it hasn't thought about it yet.
Right. The model hasn't had the space to process the intermediate logic.
So by forcing it to use a sketchpad, say I tell it, first, list out the key legal arguments in a scratchpad section. Then, cross-reference those arguments with the transcript dates. Only after you have done that, output the final summary.
Yes, perfect.
By making it physically print out those reasoning tokens first, those reasoning tokens become part of the context window for the final answer.
That is the genius of autoregressive generation. The model literally reads its own output.
That is wild to think about.
By forcing the LLM to output its intermediate reasoning, you are changing the mathematical probability distribution of the final tokens it generates. It is much more likely to generate an accurate summary if the tokens immediately preceding that summary are a perfectly extracted list of facts.
So you aren't just making it easier for a human to read the logic. You are providing the mathematical stepping stones the model needs to autocomplete the correct final answer.
Exactly. You're building the bridge while walking on it.
Okay, so we have our end-shot examples, we have our sketchpad, but if this LLM is part of a larger software product, I can't just have it spit out a beautiful conversational paragraph, right?
Right, because other code needs to read it.
Yeah, if my database expects a user ID, a date, and a categorization tag, the LLM needs to output strict, parsable data. And the sources mention using formats like XML or JSON, but they specifically highlight tools like Instructor for API calls or outlines for self-hosted models.
Yeah, this goes back to Postel's law from early network engineering.
Oh, what's that?
Be liberal in what you accept from the user, but conservative and strict in what you send to downstream systems.
Makes sense.
If your downstream database needs JSON, and the LLM decides to be helpful and add, like, here is your JSON data at the top of the response.
Oh man, the parsing script just completely breaks.
Yep, and your op crashes. So tools like Instructor and Outlines, they don't just politely ask the model to format things correctly. They use something called constrained generation.
Constrained generation, how does that stop the model from adding the polite chatter? Because they love to chat.
They do. Well, when you run a self-hosted model with a library like Outlines, you actually provide a formal grammar. It's a strict set of rules for what characters are allowed to be generated next. So as the model calculates the probabilities for the next token, the library forcefully zeroes out the probability of any token that violates the JSON structure.
Wait, literally zeroes it out?
Physically makes it impossible. It cannot output the letter H for here is your data if the grammar dictates that the next character absolutely must be an open bracket.
Wow. So you are basically reaching into the engine and cutting the wires to the hallucination machine. I love that.
It's very effective.
But here is where I want to challenge the prevailing logic a bit, because we are talking about adding 5 diverse examples and a multi-step sketchpad and explicit JSON formatting rules and tool use
It
examples.
adds up.
It really does. This brings up a concept from traditional software engineering called the God object anti-pattern. Like we're building a Frankenstein prompt.
Yes, the mega prompt.
Why do developers keep cramming 3,000 tokens of instructions into one giant prompt, hoping it will magically handle every edge case? Doesn't the model just get overwhelmed by all that text?
It absolutely gets overwhelmed. And the phenomenon you're describing is known technically as attention dilution. The source material highlights this exact scenario as GoDaddy's #1 lesson from building with LLMs over the past year.
GoDaddy. Okay, so they host millions of small business websites, so they must be dealing with massive scale and every edge case imaginable.
Oh, entirely. And their engineers found a really tragic irony. They would start with a simple prompt that worked well for, say, 80% of tasks.
Right.
Then a weird edge case would pop up, so they added a new instruction to handle it. Then another edge case, so they added a new chain of thought rule. And eventually, they had a monstrous multi-page prompt.
And what happened? It just stopped working.
Worse. The Frankenstein prompt actually performed worse on the common, straightforward task than the original
Wow.
simple prompt did.
Oh, because of the attention dilution.
Exactly.
If the attention mechanism in a transformer model has to spread its mathematical weight across 3,000 tokens of complex, contradictory instructions, it just loses focus on the core task.
It forgets what it's supposed to be doing. So the solution they advocate for is purely modular programming.
Break the tasks down.
Yes, you do not build a single catch-all prompt for a meeting summarizer. You build prompt A, which is a small, highly focused instruction whose only job is to extract key decisions from the transcript into a JSON list. That's it.
Okay, very narrow scope.
Then, your code passes that JSON list to prompt B, whose only job is to check those extracted decisions against the original text to ensure no hallucinations occurred.
A verification step.
Right. Then, you pass the verified list to prompt C, which generates the readable summary.
Which means if the final summary sounds weird, I know exactly which of the 3 prompts is broken. I don't have to tweak a God object and pray I didn't break something else in the process.
You isolate the variables. It's just good engineering.
Okay, so now everything we've talked about so far is just talking to the model. But the most critical part of an enterprise application is giving the model new information.
Right, the data pipeline.
And that brings us to information retrieval, specifically the huge battle between RAG retrieval augmented generation and fine-tuning.
This is a huge debate.
It is the great debate in every corporate boardroom right now. If a company has a mountain of proprietary data, like HR policies, financial histories, customer logs, the instinct from the executives is always, we need to train our own AI, we need to fine-tune a model so it memorizes our specific company.
That's the reflex, yeah.
But the other option is R, where you basically just use a search engine to find the relevant document, paste it into the prompt, and say, hey, read this and answer the user's question. And the authors of this guide take a very hard stance here.
They are totally definitive. For injecting new knowledge, you must prefer RAG over fine-tuning.
Really? No exceptions.
Basically none for general knowledge. They cite recent research comparing RAG against unsupervised fine-tuning, and R consistently outperforms it for factual recall.
And if we think about the actual mechanics of fine-tuning, that makes sense because fine-tuning updates the actual weights of the neural network. And those weight updates are, they're blurry, they're statistical nudges.
Very blurred.
You can't guarantee the model will perfectly memorize a specific product serial number just by showing it during training a few times. Plus, there is the issue of catastrophic forgetting.
A critical flaw in fine-tuning. When you update the weights to force the model to learn your new HR policy, you inadvertently disrupt the weights that govern its general reasoning capabilities.
So it learns the vacation policy, but suddenly forgets how to do basic math.
Essentially, yes. It learns your policy but becomes worse at basic logic.
And what happens when that HR policy changes next week? With fine-tuning, you'd have to run an expensive retraining job all over again.
Right.
But with Corrag, the model's brain stays completely untouched. You just update the text file in your database.
The authors use a brilliant manufacturing analogy here. They talk about the Toyota andon cord.
Oh, I've heard of this.
Yeah, in a Toyota plant, any worker on the assembly line can pull a physical cord to stop the entire line if they spot a defect. It's an immediate, localized intervention.
So how does that apply to AI?
Well, with AROG, if you realize a document in your database has toxic content or biased language or is just blatantly incorrect, you can pull the andon cord. You literally just press delete on that specific text file.
It's gone.
The model will never see it again, instantly.
Try doing that with a fine-tuned model. I mean, trying to make a neural network unlearn a specific toxic document that's been baked into its weights, that's an unsolved research problem.
It's a massive, expensive nightmare.
Okay, so R is the undeniable winner for knowledge. But to make R actually work, you have to be able to retrieve the right document in the first place.
Yes, retrieval is the hard part.
Right. And if you watch any AI tutorial on YouTube right now, they all tell you to use vector embeddings, semantic search.
Taking the conceptual meaning of a user's query and mapping it to the conceptual meaning of a document in a high-dimensional mathematical space.
Right, which sounds like absolute magic. But the text comes with a massive flashing warning sign about relying purely on embeddings. They say, do not abandon traditional keyword search, do not abandon BM25.
Yes.
Why are they defending decades-old search technology?
Because the reality of embedding space is that it is incredibly noisy.
Yeah.
You have to consider the insights from Baing Liu, who is the CTO of SourceGraph, and Aravind Srinivas, the CEO of Perplexity.ai.
Okay, and these are people whose entire businesses rely on retrieving information accurately.
Exactly. And they both explicitly warn that nearest neighbor search with naive embeddings yields poor results.
Yeah.
They say vector embeddings do not magically solve search.
Let's break down why that is. Because if I understand BM25, which is essentially the algorithm that has powered regular search engines for years, it works heavily on TF-IDF, term frequency inverse document frequency.
Right.
It looks for exact keyword matches, and it gives more weight to rare words. So if I search for the word Ilya, BM25 knows that Ilya is a rare word, so any document containing it is probably highly relevant.
Precisely. Now, contrast that with vector embeddings. An embedding model squashes a document into an array of, say, 1,536 numbers, representing its broad meaning.
Okay.
It captures the vibe of the document. It knows that the word dog and puppy are conceptually similar, but it is notoriously bad at exact string matches for highly specific nouns, IDs, or acronyms.
Oh. So if a user types a query looking for an exact error code like error 404B, the semantic search might completely miss the document that contains that exact code because it's just looking for documents with the general meaning of a network error.
And think about the user psychology there. After 20 years of using Google, users expect keyword exactness.
Right.
If they type a specific name or an acronym like RAG or a model ID like Claude 3 Sonnet, and the search system misses it because the mathematical cosine similarity wasn't close enough, they get incredibly frustrated.
The tool just feels broken to them.
Exactly.
So if semantic search is great for broad concepts and synonyms and BM25 is necessary for exact matches, I'm assuming the solution is to just smash them together.
Hybrid search. It is the absolute gold standard for production RGAC right now. You run the BM25 keyword matching for the obvious hard exact matches, and you run the vector embeddings in parallel to catch synonyms, spelling errors, and broader conceptual overlap.
And then you just merge them.
Yeah, you use a ranking algorithm to merge the two lists of results into one final context window.
Okay, let me throw a wrench into this entire RAG conversation. Because the ground is shifting beneath us very quickly.
Oh, always.
We are seeing models hit the market right now, like Google's Gemini 1.5 Pro, with a context window of up to 10 million tokens.
That is massive.
It is. And I am seeing critics on social media claiming that this fundamentally kills R. Their argument is, why bother building this incredibly complex hybrid search and retrieval system when I can literally just dump my company's entire Google Drive, every PDF, every single code base, into the prompt every single time I ask a question? Doesn't a massive context window make retrieval obsolete?
It is a very seductive idea for sure.
Yeah.
But the authors of this guide systematically dismantle it.
Do they?
Well, first, there is a fundamental computational reality regarding the transformer architecture, which is the underlying engine of all these models. During inference, the time complexity of the attention mechanism scales quadratically in basic models.
Ooh.
And even with optimizations, it still scales linearly with context length.
Let's translate that time complexity for the listener. The attention mechanism means that every single token in the prompt has to mathematically compare itself to every other token in the prompt to understand the overall context.
Correct. So if you double the number of tokens, you aren't just doubling the work. In many architectures, you are quadrupling the computational math required.
Wow.
Even with the best linear optimizations, the basic fact remains. The more tokens you stuff into the prompt, the more compute you burn, and the more money you pay every single time you hit enter.
So if I dump my entire company database into a 10 million token prompt just to ask, hey, what time is the all hands meeting today? I might be paying like $20 for that single query.
Exactly. And the text uses a perfect hardware analogy here. Imagine you buy a supercomputer with massive amounts of RAM. Say, enough RAM to load your entire hard drive into active memory all at once.
Okay.
Do you throw away your file system? Do you delete your folders? Of course not. You don't load a terabyte of data into RAM just to read one tiny text file.
That is such a clarifying way to look at it. A massive context window is just massive RAM. You still need the filing system, the RAG, to find the right file efficiently.
Exactly. And beyond the sheer cost, there is the issue of cognitive distraction for the model itself.
Right.
Even if a model can technically ingest 10 million tokens without crashing, we do not have convincing data that models can effectively reason over all that context without getting totally lost.
Oh, the needle in a haystack problem.
Right. There is a well-documented phenomenon called lost in the middle, where models perfectly recall the very beginning and the very end of a massive prompt, but completely ignore the information buried in the center.
Just glosses right over it.
Yeah. So if you don't have a good retrieval system to filter the data first, you risk overwhelming the model with irrelevant distractors. Good retrieval isn't just about finding data. It's a critical filter for noise.
So Aragi isn't going anywhere anytime soon. We absolutely have to build these filing systems. All right, so let's take stock of where we are. We've established the tactical base. We are using focused, modular prompts. We are using a sketchpad for reasoning. We have hybrid search, retrieving the exact right documents without overwhelming the context window.
The foundation is solid.
Right. But once you have those pieces, you realize pretty quickly that passing a single prompt through an LLM is still, well, it's a gamble. Sometimes it works beautifully, sometimes it completely hallucinates.
Which brings us to the operational reality of stringing these calls together. We have to shift our mindset from writing prompts to engineering workflows.
And the source material points to a fascinating case study here with a system called AlphaCodium.
Yes, AlphaCodium.
They were trying to get GPT-4 to solve competitive programming challenges. Now, writing code for competitive contests is notoriously difficult for AI because the logic is complex and the edge cases are brutal.
Very difficult.
Yeah.
And when they tested GPT-4 with a standard single zero-shot prompt like just pasting the problem and asking for the code, the model had an accuracy of about 19%.
Less than 1 in 5, not great for a production system.
No, but simply by shifting the exact same underlying model to a step-by-step multi-turn workflow, they boosted that accuracy to 44%.
Wow.
They more than doubled the performance without changing the model, without fine-tuning, just by changing how the system operated.
Walk me through that workflow. What exactly is the system doing to get that massive bump?
They forced a highly structured sequential process. First, the AI is prompted to merely reflect on the problem and describe it back. It's not allowed to write code yet.
It's just summarizing the problem.
Right. Then a second prompt asks it to reason about the public test cases provided. Then a third prompt asks it to generate multiple possible solutions in plain English.
Okay, brainstorming.
Then another prompt ranks those solutions. Then it finally generates code. But it doesn't stop there.
There's more.
Oh yeah. The system then prompts the AI to generate synthetic adversarial test cases to try and break its own code. Finally, it iterates on its original solution based on the failures of those synthetic tests.
It's literally acting out the entire scientific method. Hypothesis, testing, review, iteration, and all of this is hidden from the user who just sees the final, highly accurate code.
Exactly.
But this brings up a massive debate around the concept of AI agents, because everyone wants to build an autonomous agent right now. Hey, AI, go research my competitors and build a slide deck. But the authors stress that agent workflows need to be highly deterministic.
Very deterministic.
What does that actually mean when the model itself is probabilistic?
It means you cannot just give an AI a vague, open-ended goal and let it invent the steps on the fly. Because the LLM is non-deterministic, meaning it might give a slightly different answer every time you run it. Every step it invents has a small probability of failing. And in a multi-step autonomous process, those probabilities of failure compound exponentially. If step 1 goes slightly off the rails, step 2 is doomed, and by step 10, the agent is hallucinating wildly.
So how do you actually constrain it?
You have to treat the AI agent like a junior engineer. If you manage a junior developer, you don't give them a vague objective, cross your fingers, and walk away for a week.
I mean, hopefully not.
Right. You give them a clear goal, and you require them to submit a concrete executable plan for approval first. In AI architecture, the most reliable agent systems force the LLM to produce a deterministic plan, often represented mathematically as a directed acyclic graph, or a DAG.
Let's break down what a directed acyclic graph is for the listeners, because that's a heavy computer science term. A graph is just a flowchart of nodes and connections. Directed means the flow only goes in one direction, so step A points to step B. And acyclic means there are no cycles, no loops. Step B cannot point back to step A.
That is the critical part, the lack of loops.
Huh.
By forcing the AI to generate a DAG before it takes any action, you are ensuring it establishes a clear, finite, one-way path to the goal.
Okay.
It physically cannot get stuck in an infinite reasoning loop, where it endlessly researches the same topic over and over, which is a very common failure mode for open-ended agents. You lock in the plan deterministically,
Right.
and then the agent simply executes the nodes.
Okay, I want to pivot slightly to a very specific operational setting that comes up all the time when developers are building these workflows, and that is temperature.
Temperature.
Let's say I'm building an e-commerce feature that recommends products based on a user's past purchases. I run my prompt, but the LLM keeps recommending the exact same 3 boring, highly obvious items. And my product manager says, hey, we need more diverse recommendations. The immediate developer instinct is just go into the API settings and crank up the temperature parameter. Doesn't higher temperature make the AI more creative?
This is a massive trap that teams fall into constantly. To understand why it's a trap, we have to look at the math of what temperature actually does to the model's logits, which are its raw output scores.
Okay, let's get into the math.
When a model predicts the next word, it generates a probability for every single word in its vocabulary. The sockmax function turns those scores into percentages.
So the word apple might be 80% likely, banana 15%, and spaceship 0.0001%.
Correct. When the temperature is set low, the math exaggerates the differences, making the model almost always pick the safest, most likely word, which is apple. Increasing the temperature parameter mathematically flattens that probability distribution curve.
Meaning it brings the 80% down and the 0.001% up.
Exactly. It means statistically, less likely words get chosen more often.
Wait, so if I crank the temperature, I'm not making the model smarter or more diverse in its reasoning. I'm just mathematically forcing it to pick weird, low-probability words?
Yes,
That sounds like a recipe for hallucinations.
that is exactly what happens. If the temperature is too high, the model might start generating grammatical gibberish, or worse, hallucinating products that don't even exist in your catalog.
Oh, that's bad.
Or it might still fixate on the same highly likely items, but just describe them using bizarre adjectives because you forced it to pick less likely words. A high temperature introduces chaos, not strategic diversity.
So how do we actually achieve diversity, getting different, interesting product recommendations without descending into absolute madness?
Well, the authors offer a suite of brilliant deterministic engineering tricks. First, just shuffle the order of the historical data you feed into the prompt.
Just shuffle it.
Yeah. The LLM's attention mechanism is highly sensitive to token position. If you shuffle the user's past purchases in the input, the attention weights shift naturally, and the output will vary safely without ever raising the temperature.
You change the input to change the output? I love that. What else?
Second, maintain a cache of recent outputs. Keep a running list of what you've already recommended to the user. Then instruct the LLM specifically in the prompt to avoid suggesting items from that recent list.
Okay, explicit instruction.
Or don't even bother prompting it. Just programmatically reject the API output if it's a duplicate and silently resample.
You force the diversity through hard engineering logic, rather than relying on the model's chaotic creativity.
Exactly. And third, you can subtly tweak the phrasing of the prompt itself. In one run, tell the system, pick an item the user would love using every single day. On the next run, change it to, select a product they would be excited to give as a gift to a friend.
Oh, that's smart.
That subtle shift in context steers the model into entirely different areas of its latent space, but it does so safely and predictably.
That is incredibly practical. Don't touch the temperature. Touch the engineering. Now, let's move to what is universally acknowledged as the scariest word in AI engineering right now. Evils. Evaluation.
Yeah, evils are tough.
We have our prompts, we have our workflows. How do we actually know scientifically if any of this is working?
It is the hardest part of building with LLMs because the outputs are fundamentally open-ended. I mean, if you write a traditional software function to add 2 numbers, the answer is always 4. You can write a unit test for that. But how do you write a unit test for a generated paragraph about corporate strategy?
You can't just check if string A equals string B.
You cannot. So the authors recommend a layered approach. You start simple, with assertion-based unit tests drawn from real production samples.
So we aren't grading the poetry or the nuance of the response quite yet. We are just checking hard facts.
Yes. You build a suite of automated tests that trigger every single time an engineer tweets a prompt. Did the model output valid JSON? Did it stay under the 500-word limit? If it generated code, does the code actually compile and run without syntax errors? Did it remember to include the user's name? These are deterministic assertions.
But eventually you do have to evaluate the actual quality of the language. And this brings us to a highly debated topic, LLM as judge.
Yes, using LLMs to grade LLMs.
Using a giant model like GPT-4 to read the outputs of your smaller models and grade them. I know there was massive skepticism about this a year ago. People thought it was just AI marking its own homework.
There was a lot of skepticism, but the data over the last year is actually very clear. When implemented correctly, LLM as judge works remarkably well and correlates highly with human preferences.
Oh, really?
Yes. But the secret is in how you ask the judge to grade. You cannot just give the judge a single output and say, score this on a scale of 1 to 10, because it's entirely too subjective. What is the mathematical difference between a 7 and an 8? The model's baseline shifts constantly. Instead, you must use pairwise comparisons.
Pairwise comparisons, meaning you show the judge model A's answer and model B's answer side by side and ask, which of these two is better based on this specific rubric?
Exactly. It is a much more stable mathematical operation for the model. However, you have to control for position bias.
Position bias.
Yes, language models read left to right, top to bottom. They have a documented arbitrary bias toward preferring whichever option is presented first in the prompt, simply because it anchors their attention.
Oh. So to fix that, you have to run every comparison twice.
You do.
Oh.
You ask which is better, A or B, and then you swap the order and run a second prompt asking which is better, B or A. Only if the judge picks the same underlying answer both times do you record a true win.
That's clever.
And crucially, just like with our earlier prompts, you must force the judge model to use a chain-of-thought sketchpad to explain its reasoning before it outputs the final verdict.
This sounds computationally heavy, but it makes sense that it's the only way to get a scalable baseline. But there is a point where you still need human intuition, right? The authors mention a brilliant mental model for human evaluation called the intern test.
It is the ultimate sanity check for your context window.
Yeah.
Before you blame the model for failing a task, ask yourself, if you took the exact input you are providing, the prompt, the retrieved documents, the system instructions, and you handed that exact package of text to an average college intern, could they complete the task successfully?
That is so revealing. If the answer is, well, no, the intern couldn't do it because they wouldn't know the background context of this client, then boom, you've identified your problem.
Exactly.
It's not that the LLM is stupid, it's that your R pipeline failed to retrieve the necessary background context.
And conversely, if the intern could do it, but it would take them a full week of intense multi-step research and cross-referencing.
Then you are asking the language model to do entirely too much in a single prompt.
Right. You need to break the workflow down into smaller chunks.
It grounds the expectations perfectly. But as we get obsessed with metrics and evils, we run headfirst into a massive trap. Goodhart's law. When a measure becomes a target, it ceases to be a good measure.
This is one of the most critical warnings in the entire guide. The AI industry is currently obsessed with benchmarking. We create these synthetic tests to prove our models are getting better. But if we optimize the system purely to pass the tests, we can actually destroy its performance on real-world, messy human tasks.
And the authors highlight the specific danger of the needle in a haystack test, or the NIH test.
Yes, the needle in a haystack. Every AI lab is bragging about this right now. They publish charts saying, our new model found the needle in a 1 million token haystack with 99% accuracy.
For context, the standard NIH test involves taking a massive document, say a huge legal repository, and hiding a completely random phrase inside it, like the special magic city number is 42.
Right.
Then you prompt the model to answer, what is the special magic city number? If it retrieves 42, it passes.
It proves that the model's attention mechanism can scan a massive context window without losing small details.
But the authors ask a deeper question. Does that rote memorization test actually translate to useful reasoning? Because in the real world, users rarely ask for isolated, random trivia. They ask for synthesis, they ask for summaries.
Exactly. And the guide shares a specific honestly hilarious and terrifying experiment regarding this.
Oh, the pizza one.
Yes, they set up a practical needle in a haystack test using actual transcripts of doctor-patient interactions. The core task was to see if the LLM could read the transcript and accurately summarize the patient's medical condition and current medications.
A very standard, high-value enterprise task.
Very standard. But then to test the needle capability, they injected a completely random, out-of-context phrase into the middle of the medical transcript.
They inserted a phrase about pizza ingredients. The secret ingredients needed to build the perfect pizza are espresso-soaked dates, lemon, and goat cheese.
Which, just as an aside, sounds like an absolute culinary disaster.
It sounds terrible. But they stick this irrelevant pizza recipe into a serious medical transcript. What happens when they ask the model to summarize the patient's visit?
Well, the baseline model struggled with the pizza needle. Its recall on the actual medical facts was high, around 80%, but it totally ignored the bizarre pizza recipe, scoring around 30% on questions about it.
Okay.
Now, an engineer looking purely at the NIH benchmark would say, "This is unacceptable. We must optimize the prompt and the retrieval to ensure it never misses a needle."
But wait, if I'm a doctor reading a patient summary, I want the AI to ignore the pizza recipe. If the patient went on a random tangent about goat cheese, that shouldn't be in the final medical summary.
Exactly the point. Here is the crucial insight from the authors.
Yeah.
If you over-optimize your system so that it perfectly captures that ridiculous pizza needle every single time, you actively degrade its ability to do its primary job of synthesis.
Because you are training the attention mechanism that every single sentence, no matter how disjointed or irrelevant, is of equal critical importance.
Yes. You are destroying its ability to filter. If an LLM is heavily prompted or fine-tuned to attend to every detail, just in case it's a hidden needle, it loses its capacity for abstraction.
That makes total sense.
When asked to summarize a complex corporate meeting, an over-optimized model will start including distracting tangents, jokes, and useless trivia because it's been taught that everything might be a needle. Overemphasizing that specific benchmark actively hurts real-world performance.
The trade-off between retrieval and synthesis is a zero-sum game. That is a profound insight, and it perfectly transitions us to the next layer, operationalizing the magic.
Let's do it.
Because we have our evils now, we understand the trade-offs, but what happens when this system actually hits the real world? The day-to-day reality of running these models in production requires an entirely different philosophy.
It requires a philosophy that the authors sum up using the Japanese business term genchi ginbutsu, which translates roughly to real things, real places.
It's a foundational concept from the Toyota production system, right? Go to the actual factory floor to see what's happening.
Exactly. In software, it means look at your actual data logs every single day.
There is no substitute for human eyes on the logs. You cannot rely purely on the automated assertions or the LLM's judge metrics we just talked about.
The authors insist that developers must spend time reading random samples of real user inputs and the model's outputs daily, because if you don't, you will fall victim to criteria drift.
Let's define criteria drift, because the model's weights aren't changing in production, right? So the model isn't drifting.
No, the model isn't drifting. You are.
I am.
Yes. Your standards evolve. When you first launch an AI app, your baseline definition for a good output is incredibly low. You're just thrilled that the system didn't crash and that it generally answered the question.
True, the magic is still fresh.
But as you and your users interact with the system hundreds of times, your expectations rise. You start noticing subtle tonal issues. Maybe the AI is a bit too condescending. Or you notice formatting quirks or slight factual inconsistencies that you would have ignored on day one.
So my criteria for what constitutes a successful interaction drifts upward over time.
Yes. And if you aren't looking at the real data daily, your automated tests, which are written based on your day one criteria, will report that everything is 100% fine.
Your dashboard will be entirely green while your actual users are churning and abandoning the product because it feels clunky and annoying.
Exactly. You have to update your evils to match your drifting criteria.
And looking closely at the data is especially critical when you are forced to migrate to a new model. The guide states very clearly that migrating prompts across different models is incredibly painful.
It is the single biggest headache in AI engineering right now. The mantra is, changing anything changes everything.
Oh, wow.
You might naturally assume that taking a perfectly tuned, highly successful prompt from an older model like GPT 3.5 and moving it to a newer, much more capable model like GPT-4 will just magically improve your results.
A rising tide lifts all boats, right? A smarter model should just execute the old prompt better.
It rarely works that way. The new model has different weights, a different latent space, and a different attention mechanism. A prompt that perfectly constrained the older model might confuse the newer one.
Really?
The authors cite a stark example from a company called VoiceFlow. They didn't even change from 3.5 to 4. They just upgraded from one minor version of GPT 3.5 to a slightly newer release of GPT 3.5.
A patch update, essentially.
And they saw an immediate 10% drop in accuracy on their core intent classification task.
10%, just from a minor version bump in the background.
This is why the authors emphasize, you must always pin your model versions. When you use an API from OpenAI or Anthropic, do not just point your code to the generic, GPT-4 endpoint that auto-updates silently in the background.
Because it'll break everything while you sleep.
Yes. You must pin your code to a specific release hash, like GPT-40613. You ensure the mathematical weights never change without your explicit permission. And when you do decide to migrate to a newer version, you have to treat it like a major software migration. You run your entire evaluation suite, retune your prompts, and verify the data manually.
Okay, but speaking of models, I want to talk about the sheer size of what we are running, because right now, there is an absolute obsession with size.
Bigger is better. That's the prevailing thought.
Right. Everyone wants to drive a Ferrari, everyone wants to use GPT-4 Opus or Claude 3.5 Sonnet or the absolute largest Llama model for every single task. But I keep thinking, sometimes a bicycle is infinitely faster, cheaper, and easier to park if you were just going down the street to buy milk. We don't need a massive trillion-parameter Ferrari for every API call. Should we be advocating for smaller models?
The authors are aggressive advocates for the bicycle approach. Their rule is, choose the smallest model that gets the job done. The massive frontier models are amazing for prototyping. They're highly forgiving and can figure out your sloppy prompts.
Right, they can guess what you mean.
But once you prove a specific feature is actually feasible and valuable to users, your immediate next job as an engineer is to see if a much smaller model can match that performance.
They give a really compelling example of this regarding hallucination detection, don't they?
Yes, they looked at the task of classifying whether a piece of text contained a hallucination. They found that a tiny, specialized model, specifically a Distilbart model, with only 400 million parameters, when fine-tuned purely on high-quality open-source classification data, could identify hallucinations with massive accuracy.
400 million parameters is tiny. You could run that on a laptop?
You could, and because it's so small, it performs the task faster and at less than 5% of the cost of sending that same text to a massive general-purpose frontier LLM.
Less than 5% of the cost. If you are running millions of queries a month, that is literally the difference between a profitable business and bankruptcy.
And the math is often surprising. A tiny model, when paired with a highly structured prompt that includes 10 perfect examples, will routinely beat a massive trillion-parameter model that is only given a zero-shot prompt. Engineering efficiency beats raw size in production.
And efficiency doesn't just apply to the compute costs. It extends to how the human user actually interacts with the product. The guide spends a lot of time on product design and the human-in-the-loop paradigm, or HITL.
Yes, human in the loop.
The core advice that jumped out at me is a bit controversial. Do not just build a generic chatbot.
Chatbots are often a lazy user experience paradigm. When you just give a user a blank text box, you are pushing all the cognitive burden onto them.
They have to figure out what to type.
They have to figure out what the system is capable of, they have to learn how to prompt engineer, and they have to endure the latency of waiting for the response. Instead of a blank box, the authors advocate for the centaur chess approach.
Centaur chess. The concept where a human player pairs with an AI engine to compete. Historically, a human-AI centaur team will consistently beat both a solo grandmaster and a solo supercomputer. It's about synthesis.
Exactly. Applied to software design, the AI shouldn't try to replace the human workflow entirely, and it shouldn't just silently execute tasks in the background where the human can't verify its logic. The AI's job is to seamlessly accelerate the human.
Let's use the guide's example of e-commerce categorization. Imagine you are building a platform where third-party sellers upload hundreds of new products a day, and those products need to be categorized into the correct departments like home goods, electronics, apparel.
You basically have 3 UX choices here.
Yeah.
Option 1, you make the human seller do it all manually through a massive, tedious drop-down menu, and maybe you use AI later to check for errors. That's slow and frustrating.
Yeah, no one wants to do that.
Option 2, you let the AI completely take over. The seller uploads a picture, and the AI silently categorizes it in the background. The problem there is that the AI will inevitably make a mistake, and you will end up with embarrassing errors like a blender listed in the baby clothing section live on your site.
And option 3, the Centaur approach.
Option 3. The AI analyzes the uploaded product in real time and actively suggests the category right there in the user interface. We think this is home goods to kitchen appliances.
Okay.
The human seller simply reviews the suggestion. If the AI is right, they click a single button to approve it. If the AI is wrong, they manually correct it via the dropdown.
This is a brilliant UX for 2 reasons. One, it drastically lowers the cognitive load on the user. They don't have to search through menus. They just have to exercise editorial judgment, which humans are great at.
Yes, editing is easier than creating.
But 2, and this is the really powerful part, this UI generates perfectly labeled, highly accurate training data for you.
You are building the data flywheel. Every single time a user clicks approve on a suggestion, they just generated a verified positive data label for your system. Every time they correct a suggestion, they generate a negative label followed by the correct positive label.
That's incredibly valuable.
You capture that exact interaction data, store it, and use it to fine-tune your smaller models or improve your average retrieval tomorrow. The users are literally training your system for free just by using it.
This is the exact paradigm that made GitHub Copilot so massively successful, isn't it?
It is the ultimate Centaur product. Developers love Copilot because it acts as a brilliant, hyper-fast assistant that suggests code completions in real time. It doesn't try to lock them out and write the entire application autonomously.
It centers the human editor, reduces their typing burden, and constantly learns from which suggestions they accept and which they delete.
Exactly.
Okay, we have covered the tactical trenches, and we've mapped out the operational workflows. We are now zooming way out. We are stepping into the C-suite, the founder's office, the final layer. Strategy.
The big picture.
How do we make sure our company doesn't get totally outmaneuvered? Where should an organization actually spend its capital so it doesn't become completely obsolete in 6 months? The authors start this section with a highly opinionated, incredibly stark warning. No GPUs before PMF. No buying graphics processing units before you have unshakable product market fit.
It is a controversial take, but it is forged in the fire of the last year. The authors note that billions of venture capital dollars have been effectively torched by companies deciding that they need to train their own foundational AI models from scratch before they even know what product they are selling to the customer.
It's the allure of the deep tech moat. Founders think if we rely on OpenAI, we're just a wrapper. But if we train our own massive model, we own the intellectual property. But training from scratch is a massive distraction.
Almost always. The text highlights a cautionary tale. Bloomberg GPT. This was an LLM trained specifically for financial tasks, utilizing Bloomberg's vast proprietary data. It was a heroic, monumental engineering effort.
I remember when that was announced.
They dedicated 9 full-time, highly paid researchers and engineers to it. They trained it on 363 billion tokens of data using massive compute clusters.
A staggering amount of money and time.
And yet, within roughly a year of its publication, Bloomberg GPT was completely outclassed on those exact specialized financial tasks by general-purpose frontier models like GPT 3.5 and GPT 4.
Ouch. So all that time, all that capital, all that bespoke engineering just washed away by the next general update from a massive lab.
Precisely. The frontier labs are spending billions of dollars on compute. You cannot compete with them on generalized intelligence. Unless you are building something incredibly fundamentally specialized, like Replit, building a bespoke model for code generation training from scratch is a trap.
And even fine-tuning existing open-source models is heavily driven by FOMO, the fear of missing out.
Founders want to beat the wrapper allegation so badly, but the authors advise, do not fine-tune until you've proven mathematically that you absolutely have to. Start with the inference APIs. Use prompt engineering. Validate that human beings actually want to buy and use your product first.
Only spend money on GPUs when your API costs get too high or your latency gets too slow.
Exactly.
But wait, I have to play devil's advocate here. If we shouldn't build our own models and we're just relying on APIs from Anthropic or Google or OpenAI, and those APIs get demonstrably better and dramatically cheaper every single month, what exactly is our product? Aren't we just building sandcastles on the beach waiting for OpenAI to wash them away with their next update?
That is the existential question of the AI era. And the author's synthesis of this problem is profound. The paradigm shift is this. The model is not the product. The system around the model is the product.
the system.
Yes, if you think your competitive moat is having a slightly clever prompt or having fine-tuned a set of neural network weights, you are vulnerable. The true moat is your custom evaluations that ensure your software achieves 99.9% reliability in your highly specific domain.
Okay, I see.
The moat is your guardrails that catch the weird, toxic edge cases specific to your industry. The moat is your caching mechanisms that make your application incredibly fast. And most importantly, the ultimate moat is your data flywheel. That human-in-the-loop system we discussed earlier, constantly capturing human preferences and edge cases that OpenAI and Google simply do not have access to.
It's the infrastructure, not the engine. If Ford builds a better engine tomorrow, it doesn't matter if you own the entire highway system and all the gas stations.
Exactly. And strategically, this dictates the buy versus build decision for every engineering team. The authors explicitly state, do not build LLM features you can buy off the shelf.
What's an example of something a team shouldn't build?
Do not build a custom text-to-SQL engine so your marketing team can query the database. Do not spend 3 months building a generic ARG chatbot to talk to your company's internal HR documentation.
Why not?
Those are generalized problems being solved en masse by hundreds of well-funded SaaS companies right now. Buying an off-the-shelf solution will be cheaper, faster, and better maintained. You must focus 100% of your incredibly expensive engineering R&D purely on domain-specific problems that align directly with your unique product goals.
Which brings us to the final strategic framework. To truly build a moat that will survive the next 5 years, we need to understand the overarching macroeconomic trajectory of AI costs. What actually happens to society and to software when intelligence becomes as cheap as electricity?
To understand where we are going, the authors look back to a pivotal moment in computing history. Specifically, 1971 at Xerox PRU.
The absolute legendary birthplace of the modern computing era. They invented the graphical user interface, the mouse, Ethernet networking.
But the question is, how did they know what to invent? How did they know a graphical user interface would be viable? They engaged in a brilliant exercise. They looked at technologies that were incredibly useful, but currently unfeasible economically.
Unfeasible how?
Driving a high-resolution video display in 1971 required thousands and thousands of dollars worth of RAM. It was a joke to think a regular person could afford it. But the researchers at PARC looked at the historic price trends of transistors. They mapped out Moore's law, and they accurately mathematically predicted exactly when that RAM would become cheap enough to be commercialized.
Oh, so they didn't build for the economics of 1971. They built systems for the economic reality of 5 years in the future.
And we can do the exact same exercise for large language models right now.
We can and we must. Look at the cost curves the authors have mapped out. In the roughly 4 years since the launch of OpenAI's original GPT-3 API, the cost of running an AI equivalent to the original ChatGPT dropped from $20 per million tokens down to less than 10 cents.
Yeah, $20 down to 10 cents. That is a 200-fold reduction.
It's unbelievable.
And the cost curve is actually accelerating. Meta recently released their Llama 3.8b model, which has roughly similar performance to those older frontier models, and it costs about 20 cents per million tokens to run. That represents a 100x cost reduction in just the last 18 months.
Think about the magnitude of that. Moore's law predicts a mere doubling of hardware capability every 18 months. In AI inference, we are seeing 2 orders of magnitude in cost reduction in that exact same time frame.
That is staggering. It breaks traditional financial modeling, and the authors illustrate this with a brilliant analogy about Pac-Man, which brings us back to our opening hook.
Yes, the video game simulation.
Yeah.
The authors look at a famous recent research paper where LLMs were used to generate the autonomous behavior of multiple video game characters living in a simulated town.
Yeah, they had memories, they interacted, they planned their days. It was an amazing glimpse into the future of gaming.
But it was incredibly expensive. When the paper was published in August 2023, it cost about $625 an hour in API fees to run that simulation.
Which makes it totally unfeasible for a real video game company to implement. Nobody is paying $600 an hour to play a game.
But less than a year later, due to the plummeting cost of APIs and smaller, more efficient models, that exact same simulation cost had dropped an order of magnitude to roughly $62.50 an hour.
And let's map that against historical arcade economics. In 1980, playing Pac-Man in an arcade cost you quarters, but if you map it out, It was the equivalent of about $6 an hour in today's money.
So the goal is to get the AI operating cost down to that $6 an hour mass consumer entertainment threshold.
Precisely. And if you simply extend the current halving curves of AI inference costs, the authors extrapolate that compelling LLM-enhanced gaming characters will hit that $6 an hour economic viability mark by 2025.
That is literally right around the corner. So what is the ultimate strategic lesson here for founders, for developers, for anyone trying to build something lasting?
The ultimate lesson is skate to where the puck is going. Do not build for the constraints of today's API pricing. What looks like a completely unfeasible, laughably expensive, ridiculous academic research paper today will be a premium feature in a few years and a basic expected commodity shortly after that. You must build your organization, your architecture, and your systems anticipating that raw, generalized cognition will soon be practically free.
Wow. We have covered an immense amount of ground today. Let's recap the golden path from 0 to 1 and from 1 to N based on everything these engineers have learned from a year of applied LLMs.
It's a lot to take in.
It starts in the tactical trenches. Master fundamental prompt engineering, curate representative end-shot examples, force the model to use a chain-of-thought sketchpad to alter its mathematical probabilities, avoid the Frankenstein prompt, build hybrid RG systems that combine the conceptual power of embeddings with the exactness of BM25.
Then operationalize it. Use directed acyclic graphs to constrain agent workflows, build domain-specific evaluations like hard assertions and pairwise LLM judges, but beware of Goodhart's law and the pizza needle.
Right, the pizza needle. Use those evils to design a product that keeps the human at the center of the UX, acting as a centaur, to build your proprietary data flywheel. And through it all, fiercely protect your time and capital.
Refuse the FOMO. Do not train models from scratch until you have unshakable product market fit. Build the system, not the model.
It is a rigorous playbook. It systematically replaces the intoxicating magic of the social media demo with the cold, reliable discipline of software engineering.
And it brings us back to where we started. We want predictability. We want to know that on a Tuesday afternoon when the system is under load, it works.
But I want to leave you, the listener, with a final provocative thought to mull over, building on that economic reality of low-cost cognition.
If we are rapidly approaching an era where the raw intellectual horsepower of an LLM is practically free and equally available to every single competitor in your space via an API call, then the AI technology itself ceases to be a differentiator. Everyone will have the exact same synthetic IQ at their fingertips.
Therefore, your ultimate competitive advantage won't be your code. It won't be your prompt. It will be your human taste. It will be your deep domain expertise. It will be the unique friction and the messy proprietary reality of your specific data.
So look at your own life or your own business.
Ask yourself, what highly complex, historically expensive cognitive task are you currently assuming will always be out of reach that might suddenly become affordable by next Tuesday?
It is a question that completely redefines what is possible to build.
Thanks for diving deep with us.